Make sure. Okay, hi everyone. Okay, so welcome. Your exam is on Monday, so I figured today we'd kind of do a little review of everything that we might be covering. I will also be having a review on probably Sunday morning on Zoom for an hour if you would like some last minute practice before the exam as well. But I'll put those details out probably tomorrow or Friday. And I'll just make sure Dr. Altimos makes an announcement on Friday in class. And I basically can stay here for as long as you need me. I said I would extend it for a half hour if need be. So if you have more stuff you want to ask, the time is yours. So hopefully my iPad just doesn't die and then we can stay as long as you need. Okay. Where would we like to start?
Maybe chapter 5 stuff.
Chapter 5?
I go from there.
Okay. That sounds like good for everyone else. Okay. And how are we feeling about like the stuff you had to do over spring break, fluid structures and all that fun stuff, geometries and everything there?
Pretty good, except like I guess like what you went over today, like a perfect sort of Lewis model or whatever.
Okay.
Like I don't know which one is the bonds and stuff like that.
Okay. Do you want to maybe just start there since we talked about that in class, and then we'll go back to chapter 5. Yeah. Okay. So today we were talking about like resonance structures and then just like structures in general. So resonance is going to be that keyword that you see a lot. I might be spelling it wrong, but you get the idea. Right, resonance structures are going to be how we determine what the like ideal Lewis structure is for an element. Okay, so whenever we are looking at resonance structures or the ideal, we always need to make sure that we just have some form of our Lewis structure written down. So today we talked about I think NO2 minus. Yes. Yeah. Okay, let's write out the Lewis structure for NO2 minus. How are we doing? How would we solve a Lewis structure for this one? Yeah, we just count the valence electrons. So how many total valence electrons do we have? I think 18 is correct. Yeah, 18 is correct. Let's see if I can find that. Okay, so we should have 18 electrons. Okay, what's going to be our next step? Yep, we need this central atom, and where do we go for, and how do we identify that one? Good. So whichever one is least electronegative is going to be your central atom. So out of electronegativity trend, is nitrogen or oxygen going to be more electronegative? Oxygen is going to be more electronegative, and so that means it's going to go on the outside. Can anyone tell me the trend for electronegativity? Yep, this way, right? So if we're looking at the periodic table, this corner up here is going to be your most electronegative. So as you go across, you're going to increase electronegativity, and as you go down, you're going to decrease electronegativity.
So that yes, the elements to the left will usually be the center atom.
Yes, yep. So if you have any sort of metal, that would usually be towards the center. But a lot of the times for these Lewis structures, you're going to be bonding elements like in this corner over here for the periodic table. So you just have to think about those trends between carbon and chlorine and all that fun stuff there. Okay. So another key to kind of look at for your central atom is which one you only have one of. If you only have one nitrogen and then like 3 or 4 of the other ones, that's usually the one that's going to be the center as well. So here for nitrogen, we're going to put nitrogen in the center, and then how do we connect our oxygens on the outside? Yep, and how many? You just start with 1, right? So you'll just put oxygen on either side. It does not matter where you put them. You can put them at diagonals. You can put them both pointing up. You can put them both pointing down. Does not matter, but as long, right, if you can have like this, you can have like this. Does not matter, as long as you just have one bond to each of them. Okay. So how many electrons did we use when we just made this structure here? We used 4, so how many do we have left? Awesome. And where does that go in terms of our remaining elements? Good. So we're going to complete the octet. So right now, how many atoms do our oxygens have? We have 2 electrons. And how many does our nitrogen have? 4. Good. So we're going to fill our outside atoms first. Excuse me. Those are more electronegative, so those are more likely to have the electrons. So we'll put our 6 dots around them, right? They already have 2 from the bonded, and then we need 6 more to complete its octet. How many electrons did we use here? 12. How many are remaining? 2. Where did those go? Awesome. So they're going to go on the nitrogen atom. What do we do now? Right, so now we have to try and fill nitrogen's octet. When we look at this, nitrogen only has 6 electrons. How many does it want? It does want 8. Okay, so another way that we can look at this is with our formal charges that we talked about today. I know that Dr. Alkmos gave you a formula to talk about formal charges. I don't remember what that was.
Bonded pairs minus number of non-bonded pairs. Pairs and minus 1 something.
So for formal charge, we're looking at number of valence electrons minus the number of lone pairs minus 1/2 the number of bonded. So I guess it's not really number of lone pairs, more of number of lone pair electrons. So if we were to calculate the formal charge of oxygen here, it doesn't matter which one we're using, since they look the same right now. How many valence electrons does oxygen usually have according to the periodic table?
6.
It has 6. How many lone pair electrons do we have for oxygen in our structure so far? We have 6. And then how many bonded electrons do we have?
Is the second 6 cut from 1 atom or more?
Just for 1 atom. So whenever you're doing the formal charge, you're just looking at this one here. Okay. For this one, since they are looking the same, it doesn't matter which one you're talking about. Okay, so then how many bonded or number of bonded electrons do we have? 2. Okay. So you have 6 minus 6 minus 1/2 of 2, which is 1. So what does our oxygen formal charge come out to be? -1, right? Little trick on formal charge as well. When they talk about number of lone pair electrons and number of bonded electrons, if you just count the dots in the lines, you're going to get the right answer, right? You say, how many dots do I have? 6. How many lines do I have? 1. And that's the same thing. So you don't have to worry about 1/2 or anything that way. So it's just the number of valence electrons minus the dots minus the lines. And that'll get you the correct answer too. Okay. So looking at the formal charge, we have a formal charge of -1. So that means that this oxygen has a -1 and this oxygen has a -1. What do we know about formal charges? What do we want them to be? We want them to be 0 if possible. So what can we change in order to make one of those, at least one of those oxygens have a 0 formal charge? Yep, we're going to take a double bond. So you can just kind of take one of these lone pairs and just put them right here instead. We can take this guy here and put it here. So now the structure turns into oxygen, nitrogen, oxygen. Everything else remains the same. But now we have a double bond on oxygen and nitrogen for that one. Bless you. Thank you. Okay, any questions on how we were able to get that far?
Is that it?
Yep, so now what you can say is like, is this the best structure for nitrogen or for this nitrate ion? So in order to say, is this the best, you would then go again and calculate the formal charge. So take a second, calculate the formal charge. We'll call this oxygen 1, and then nitrogen, and then oxygen 2. So let's say, okay, so we want to calculate the formal charge for oxygen 1, nitrogen 1, and then oxygen 2. Tell me if this is the best. Yes. Did we get formal charges? What do we get for that oxygen 1?
0.
0. And how'd you get that?
6 minus 4 minus 2.
Beautiful. What about that nitrogen? Also 0. How'd you get that?
5 minus 2 minus 0.
Awesome. And then what about oxygen 2? Negative 1, right? And we just saw that from the previous formal charge. Okay. So now we're saying that from this structure here, we have 0, 0, minus 1 formal charge. Is it okay that the second oxygen is a minus 1? Yeah, right? From our original compound, it's NO2 minus. So one thing to remember is that when you're calculating your formal charges, they always want to add up to whatever charge is on that compound. So if we add 0 plus minus 1, we see that we get a minus charge anyways. So that's good to go. We have the least number of elements as with a formal charge, like most of them are 0. And then any formal charges that we do have add up to the charge on our original compound. So we can say that this is a ideal structure or Lewis structure for NO2. Okay, any questions on how we determined ideal for this one?
You explain how you did that? You said that you did lone pairs minus the bond, right? What, like I was going to
Yep. So if you can see that structure up here, just fine.
Yeah.
Okay. So when we're looking at this oxygen here, we know that we have the valence electrons. So based off of the periodic table, we know that oxygen has 6 valence electrons. Okay. How many dots does this oxygen have? It has 4, right? So we have the number of lone pair electrons is 4. We have 4 dots. And then how many lines does it have?
Yeah.
It has 2, right? So that's 1/2 of the bonded electrons, right? Because we're saying that 4 electrons are being shared between oxygen and nitrogen. So we can count for 2 of them for oxygen. So we're saying that we have 2 of those shared electrons. So then we can say 6 minus 4 minus 2 is going to be 0. Okay, does that make sense? Answer your question? What other questions do we have? Okay, so we said that this structure in red here is going to be our ideal structure. Do we have any resonance structures for this guy here? See head shake, yes. Anyone else agree with yes? I agree with yes. So you can show that a resonance structure exists because we can put this double bond on this side, right? So if we took this structure and then went like this, that would be the resonance structure. We still have oxygen and nitrogen and oxygen, but this time the double bond is going to be on the right hand side. Okay, so 2 resonance structures exist for NO2 minus. Okay, what questions do we have on that? Okay, so these are our 2 resonance structures. What's going to be the bond order of your bonds here? The bond order. What's the bond order if we just look at this single bond between nitrogen and oxygen? The single bonds, what does that mean for the bond order?
What is the bond order?
So the bond order just basically tells you like how many bonds are present. Okay. So if this is a single bond, how many bonds are present? This one, this single one, just between nitrogen and oxygen, there's only 1 bond, so that's only a 1. So this bond order here is going to be 1. What about this double bond between oxygen and nitrogen? 2, right? So this bond order is 1, this bond order is 2. Okay. What questions do we have on that one? If we had a triple bond, what would that bond order be? That would be 3. Good. Okay, but we have a resonance structure that exists. So this oxygen nitrogen double bond is not always a bond order of 2. It's sometimes a bond order of what? 1, right? So if we can have a bond order of 2 and a bond order of 1, what's going to be our overall bond order, do you think? 3/2, right? So 1.5. You have 2 different options, 3 different bonds that exist. And so we can take that over 2 structures, and that's going to be 1/2. Right, so sometimes it's 2, sometimes it's 1. I usually do this by saying like, okay, I have a double bond and then I have a single bond. I can divide that by the 2 structures I have, so that's 3/2. So a bond order of 1/2. Okay, so probably our actual structure that exists is going to be this like half bond between them. I just sorted like that. Basically like 1.5 bonds between each of them. That's what that bond order of 1.5 is telling you. If you also see something with a 0.5, that means that a resonance structure does exist, right? If anything with the bond order has a decimal, a resonance structure will exist somewhere in that structure.
So we're taking a 2 + 1. That's coming from the 2 lines and then the 1 line.
Yep. So if you're looking at this bond order, you're saying, okay, this one has a double bond, so a bond order of 2.
Yep.
This one has a single bond, so a bond order of 1. So I'm going to add those 2 up and then divide that by the 2 possible structures that I have.
Okay, what about the other side of that?
So that would be the same thing, right? So yep. So this would be a 1 plus a 2 divided by the 2 structures would also give you 1.5. Yep. Okay, what other questions do we have? So this is their bond order of the overall structure. Right, so if you were to like average the 2 resonance structures you have, then you would say that you have about a 1.5 bond order. Okay, any other questions? Do you want to practice that one more time with the ideal situation? I don't know. Let me check on B real quick. I don't know if it has a charge or not.
For A, we just not this and try them.
Kind of. So you want to think of it like water, where like oxygen's your center there, and then you have the two hydrogens on the side. Set it up like that, where it's like there's one oxygen in the center, and then two are branched out from there. Oh, I'm sorry, we're not going to do this.
So do you have to like use the formula, or can you just see that the center one doesn't have 8 and then move one over?
You can, yep, that's like a shortcut. It's, I think, more for like this one, you'll have to just kind of look what we are. If the center atom doesn't have 8, then it's like, okay, I have to do something. Yeah. You're right. Yeah, I wanted a different one. The other one had a resident structure, but it was just like going to be too similar to the one, so I want to give you something a little different.
Okay, is anyone stuck? Which one are we stuck on? Second one. Okay. Do you want to do the first one together? Okay. So for our ozone or O3, what is the first thing we need to do? Yep, we want to count valence electrons. So how many valence electrons do we have with this one?
18.
18, right? Okay, we have 18 valence electrons. Okay, I kind of gave you a hint, or it's just kind of gonna look like water, but with oxygens instead of hydrogens. So this one, your central atom is just still oxygen, and then it has outside of oxygen as well. So you can put oxygen at the center and then one oxygen attached to both of them. Okay. How many electrons did we use here? Yep, we used 4 electrons. Then we have 14 left. Where are those going to go? We're going to go on the outside oxygens, right? So we're going to put those like that. Okay. How many did we use? We used 12. How many do we have left? 2. Where do those go? We go on the center oxygen. What do we notice about that center oxygen? It's not filled. So how are we going to fill that center oxygen? Double bonded. Where are we going to move that from? Doesn't matter. One of the oxygens on the outside, right? So we'll do the same thing we did last time. We'll take this one, move it here. And so now our structure turns into oxygen, double bonded to oxygen, single bonded to another oxygen. What does that structure look like? Kind of looks like this one up here, right? So they're very, very similar, right? One of them just has a nitrogen with an extra electron. This one just has an oxygen right away. Okay. So if we were to calculate the formal charge for all 3 of these electrons, we're going to call it 1, 2, 3 going across. Okay. What would be our formal charge of our oxygen 1? It would be 0. What about that formal charge of oxygen 2? See, positive 1. How do you get to positive 1? Awesome, right? We have 6 is our valence electrons of oxygen minus the 2 dots we have minus the 3 lines we have. Okay, so that should be positive 1. Perfect. Okay, and then what is that formal charge of oxygen 3? Awesome. Okay, so we have 2 formal charges this time, right? But this time it's 0, positive 1, and negative 1. What charge do we have on ozone? 0. What do our formal charges add up to? 0, right? So this is a very good structure here. Okay, does a structure exist for ozone? Yep, what is it going to look like?
The other side of the bond.
Perfect, right? We're going to take this double bond, put it on this side, so we end up as a single bond on the left and a double bond on the right. So you can say that this would be oxygen, single bond, oxygen, double bond, oxygen. Okay. And so now we have, right, oxygen 1, that looks like oxygen 3 from the beginning. Oxygen 2 looks the same, and then oxygen 3, but now looks like oxygen 1. Okay. What questions do we have about ozone? To help make a little bit more sense on that one. Yep, again, bond order would be 1.5 because we have 2 and 1 divided by our 2 structures. And then we have 1 and 2 divided by 2 would be, between our 2 structures would be 1.5 for both of them.
concept of what does bond order mean?
Yeah, so bond order is just like, it's just a funny way or fancy way to say number of bonds present. So here we have a single bond, so only one bond is present. And so that means that we only have a bond order of 1. Here we have a double bond, so we have 2 bonds present, which means we have a bond order of 2.
But in reality, you have 1.5 of both ends.
Yep, because we could have a double bond or we can have a single bond. So you average that together.
Okay.
Yep.
Thank you.
What other questions? Okay. Do you want to try CO3 on your own again, or do you have an answer for that one?
I got stuck.
Okay,
How many base electrons does carbon have again?
carbon has 4.
Okay.
So I believe we should have 24 valence electrons. Do you agree with that so far? Okay. Yes. What's going to be our central atom here? Going to be carbon. And then where are we going to put our outside atoms? Anywhere, right? Just anywhere around. It doesn't really matter the geometry, right? You can do oxygen like this if you really wanted to. I'm going to make it more, just more space. Okay. How many valence or how many electrons did we use when we bonded our atoms?
6.
Good. How many do we have remaining? 18. Where are those going to go?
On the oxygen atoms.
Good. How many did we use?
18.
18. Is this an ideal Lewis structure? Why do you say no?
Carbon is not all it's unoctane.
Perfect, right? Carbon only has how many electrons?
6.
It has 6. It wants to fill its octet. It wants 8. What are we going to do in order to fill that central atom?
One pair from the oxygen to the carbon.
Perfect, right? Same thing like we did here. We're going to take a lone pair and put it to a double bond. So I'll just take this one up here and put it to this bond over here. So now we have everyone agree? Okay.
It does give us a formal charge of negative.
Yep. And why do you say that?
Because the oxygen and the carbon both have formal charge of 0, but 2 oxygens have -1.
Awesome, right? So whenever we see an oxygen that has 1 single bond and 6 lone pairs, or I guess 6 oxygens of lone pairs, 6 electrons of lone pairs, excuse me, that'll always have a formal charge of -1. So we know that this oxygen here will have a formal charge equal to -1. This one will have a formal charge here equal to -1. This one here will have a formal charge equal to 0. And this one, this carbon here will have a formal charge equal to 0. So if we add up all of our formal charges, -1 plus -1 will equal that -2 that we have at the top. What questions do we have about that one? I have questions. Does a resonance structure exist? Yes. How many?
3.
3, right? And why is there 3 that exist?
So that double bond can be on any of the oxygen atoms.
Often, right? So we can put this double bond here, or here, or here, where it is already. So since we have 3 different resonance structures, we can write them. I'm gonna skip my actually. I'm gonna do next one. We have these 3 different resonance structures. What's going to be our bond order? 1.33. And how did you get that?
guess for each bond, they have a chance to have one bond, two bonds, one bond, and those together.
Awesome, right? So if we just look at this carbon oxygen bond here, right? This one can be a double bond, which would be 2. Can be a single bond, which would be 1. And then one more single bond here. We have 3 different resonance structures. And so we have 4/3, which is going to be 1.3. So what would have more energy, a single bond or one of these bonds in this CO3 molecule? Which one has more energy? So I like your double bond, right? So the double bond is going to have the highest energy out of the double or the single. But between just a single bond and this 1.33, that the 1.33 is going to be higher. It's like a double bond doesn't actually exist in this molecule here. It kind of all has that 1.33 bond we're talking about. Okay, but your 1.33 bond is going to be stronger than your single bond would be, which would therefore have more energy, and then which would require more or less energy to break. Require more.
They all have the same amount of energy to break, but they have more energy than a double bond. Sorry, than a single bond to break.
Yes. Yep.
Okay.
So all of these bonds would be the same in terms of energy, and in terms of length, and in terms of bond order. Any other questions? Feel a little bit more comfortable with like ideal structure, formal charge, fun stuff, Lewis structures there. Yes. Okay. Did anyone tell me what shape that would be? Electron domain geometry. How many electron domains do we have? We have 3. So what is that?
Something.
It starts off with tri, but it sounds different than tri. Sounds more like a trig.
Trigon something.
Trigonal what? Planar. Yep, it's going to be trigonal planar. So when you have 3 or 2 of your electron domains, those can always lay flat against the plane, right? So if you were to look at this CO3 molecule, you could hold it up and put it flat down on your piece of paper, right? It would lay in the same plane. So this is called an electron domain geometry of trigonal planar.
How do you know it's only 3?
Okay, we got that from the electron domains. So when we're looking at this molecule here, I tend to think of these as like groups of things. So you can draw a circle around this, this, and this. Okay, so that's 3 electron domains you're working with. If we had a lone pair, right, if we had one here, then you could draw another electron domain, right? So then you would have 4 electron domains. Okay.
Was it O3 one? Like that'd be bent, right?
Close. It's bent for its molecular geometry,
Okay.
for its electron domain geometry, but it's
still trigonal planar.
awesome, right? So for our CO3, we're saying this is trigonal planar for its electron domain geometry, and then its molecular geometry, right? You can think of the electron domain as the umbrella, and then its like category is the molecular geometry. This is still going to be trigonal planar. But for our O3 or our ozone, again, we have your 3 electron domains. We have this oxygen here, and this lone pair here. So the electron domain geometry is still trigonal planar, but its molecular geometry is now bent. Okay, so it would actually look like actually look like that. Okay, and why does it end up bent? Yep, and what do the lone pairs do? Yep, so they repel the other bonds. They take up more space than a bond would, right? If you're thinking about these oxygens in a bond, think of it as a dog with a leash and its owner, right? It can only go so far. However, if that dog does not have a leash anymore, it can kind of roam out a little bit more, right? It has a little bit more space. So it's going to push the bonds together down here, causing this angle to decrease because those lone pairs now just take up more space. A little bit more space to move. Okay. What would this angle be?
120 degrees.
Exactly.
No.
Yep. So
That's more of an estimate, right?
yep. So this one here for your CO3, this one's most likely going to be 120 degrees. And that's because we have 3 of the domains, and there's no lone pairs. And so they can kind of just stick out like the triangle would. However, when we have the lone pair, they're going to squish a little bit together. So it's going to be less than 120 degrees is really all you need to know.
Will that be the way it's in the test?
Yep.
Less than 100. Okay.
Less than 120. And I was probably either, she could ask you like equal to 120, less than 120, or the same, or greater than 120. Okay, what other questions do we have about formal charge, Lewis structures, electron domain geometry, molecular geometry? Do we feel more comfortable? Yes, already. Sweet. Okay. We want to go back to chapter 5. Or is there anything specific that people want to? Alrighty, y'all want to chapter 5.
What was it?
Mhm.
The gas lines.
That was gas law?
Okay.
Okay, what can you tell me about gas laws? Awesome. When I was taking chem in high school, my teacher would say she's a Picnic type of person. Stuck with me my whole life now. Right, PV equals nRT is going to be what? What is this called? Right, this is our ideal gas law. Hey, what is our R value here?
0.0826.
Awesome. Did I remember the units?
L over 18, yeah.
Oh,
It's 8 atmospheres liters over moles Kelvin, right?
oh,
Okay, so what does that mean for your temperature? What unit does temperature need to be in? Yep, temperature should always be in Kelvin. What does your volume need to be in? Yep. And what does your pressure need to be in?
atmosphere.
Awesome. Okay, and then you just need to have moles. So if you're given anything with like grams or given a concentration and a volume, you can use that in order to get to your moles of that solution. Right, because what is molarity concentration?
9 moles in 1 liter.
Awesome, right? Molarity is always moles over liter. So you can always get moles if you have a concentration and a volume. Okay, what else can you tell me about gas laws?
It's non-ideal.
Yeah, there's a non-ideal. We're not going to worry about that. I don't think she's going to test you on it.
Pressure and temperature are directly proportional.
Awesome.
Pressure and volume are inversely proportional.
Awesome. So as pressure increases, what happens to temperature?
Increases.
Temperature also increases. right? And if you think about like a balloon, if you put a little heat underneath it, that will expand because your gases are getting hotter, and so they're moving a little bit faster and creating more pressure, therefore expanding that temperature. Because it was more of a volume question, but think about boiling water, right? You got lid on it. That volume's not changing. And so that's what causes your water to actually boil, because the pressure reaches the atmospheric pressure. Science. Okay. What's another relationship? As pressure increases, what else happens? Good. Volume decreases. Okay, so if you were to take a basketball and squish it down to the size of a baseball, the gases in that basketball are going to increase, are going to be closer together, hitting the walls more frequently, creating a higher pressure. Okay, so as volume decreases, pressure increases.
Assuming temperature is held constant.
Yeah, these are all assuming something else is held constant. Anything else?
Is it possible to take that whole, say, volume constant as you raise temperature?
Yeah, that's what you do when you boil water.
Oh.
Anything else?
It's not regardless, it's not really a relationship, is it?
Yeah, it's not really too much of a relationship. Do you remember what that is?
It's E1 over E1 equals E2.
So that's still going to be, that's going to be Boyle's law. And that's just telling you the relationship between pressure and volume. So when we have P1 V1 is equal to P2 V2, this is just saying that, right, this is going to be equal to a constant, which is like this R value, nRT stuff over here. So as if you have a starting pressure and a starting volume, if you increase your pressure, that means you have to decrease your volume in order to keep this the same, in order to keep this relationship constant. So this is just proving this relationship here that we talked about.
So then I'm gonna get pressure. If you increase pressure, then you increase moles rate. Where is that one? Because then it goes over N over T rate.
Yeah, so there's I believe Avogadro's.
It's volume over.
So Avogadro's is volume over N is equal to volume over N. So what does this tell you? As volume increases, what happens to your number of moles? They also increase, right? So if you want to expand a balloon, right, you have to blow more air into it. You're blowing more moles of your gas into that volume or into that balloon, increasing its volume to get to the correct size. Okay, so this is saying as
Could you also
volume increases, moles increases.
I mean, I don't know if it's true. Could you also substitute pressure as pressure increases? You increase moles.
Absolutely, yeah. Right, we're just manipulating PV is equal to nRT, right? We can divide any of these by that, and we can say, right, we can get pressure and temperature, we can get pressure in moles, we can get volume and temperature, we can get volume in moles, right? All of that is going to be equal to that R constant. And so if one of them or multiple of them are being held constant, they will always be equal to each other. Righty? Is there anything else you can tell me about gas laws? Yeah, partial pressure. Awesome. Do you know what the equation or formula is for partial pressure? Or can you tell me what that means? Awesome. This is P1 over P total is equal to N1 over N total. And what else is this equal?
It escapes me.
Anyone got an idea?
Interesting.
This is called your mole fraction. Can anyone tell me what this like partial pressure is telling you? What does this formula mean? Awesome. Yeah. So, right, if you look at air, right, air is made up of a whole bunch of gases. So that's going to be your total pressure is your air. You can look at each individual component. You can say, okay, what's my pressure of oxygen? What's my pressure of nitrogen? What's my pressure of some random thing in the air, right? That pressure and divided by its total pressure will be directly proportional to the number of moles you have of those products. Right? So if you have 10 moles of air and 2 moles of that are oxygen, then you know that about 20% of that pressure that you have is going to be made up of that oxygen. Okay, questions on partial pressure or anything like that? There's another partial pressure equation. Does anyone know what that one is?
All the pressures together equals.
Awesome. Yeah. You can say that your P total is equal to P1 plus P2 plus P3, so on and so forth. So your sum of your pressures equals your total pressure. Okay, and then you can sub in any of those for the N1 over NT to get your mole fraction of all of them and yada, yada, yada. Will your mole fraction ever be greater than 1? Nope. It will be a decimal somewhere between 0 and 1. Any other questions on partial pressures? Is there anything else you can tell me about gas laws? That's pretty much it.
Anything else worth forgetting?
I was just about to look at the mock exam. Okay. Anything over here we didn't cover? I guess just this one here. So this one is a just derivative or derivation of PV is equal to nRT. So if you have the molar mass, you are able to find the density of a element, or if you have the density, you're able to find the molar mass. But I do believe that's given to you again on your exam, so you don't need to like memorize it or derive it yourself. You should be able to look at that, no problem.
So it's pressure times molar mass over then constant times temperature.
The RMS is a kinetic energy.
Yes, yep. So this over here kind of plays into gas laws as well. These are like all of your equations or constants for gas laws. So this kinetic energy is also part of your gas laws. Good job pointing that out. Okay, so we can have okay. So you have these other 3 equations. Excuse me. You have your kinetic energy. This is your average kinetic energy. So this is where a graph comes into play. Does anyone remember what that graph is called? It's on your mock exam if you looked at it. Kind of looks something
Oils?
like this. This does start with a B.
Yeah.
Kind of. This is your Boltzmann distribution.
Okay, I'm gonna draw this a little bit better. You know it. Okay, so this is a Boltzmann distribution. And this is telling you what your average molecule speed will be at certain temperatures. So this is one that is being held at the same temperature. So all molecules, or say all atoms at 25 degrees Celsius. If we were comparing helium and neon, which one would be helium and which one would be neon? The bigger one, you mean like this one? Do we agree or disagree with helium being the bigger one?
Only if they don't take this year.
Right, so let's kind of look at our equations that we have, right? So we're saying all atoms are at 25 degrees Celsius. So what does that mean about our kinetic energy between helium and neon? Are they the same or different? They're going to be the same. Okay, so once we have kinetic energy, where does that go? What can we use that in? What other formula here? It's going to be this one here, right? We're saying that we have 3RT, it's going to be 3RT here. Okay, so we can say that how fast we're going, or the VMS, is going to be equal to the square root of 3RT divided by the molecular weight. So if this 3RT is the same for both of them, do we want a low or high molecular weight in order to have a fast speed?
No.
Low.
So helium's gonna be fast.
Yep, so helium is going to be fast in comparison to neon. So if we're going faster, does that mean we're going to be this long curve or this tall curve?
Helium's a tall curve.
Helium's actually going to be the long curve. So this would be your distribution of elements going at a certain speed. So I guess I probably need to give you access.
Oh.
But this is like how this is the RMS. Okay, so your helium is going to have a greater probability of moving faster than any of your neon atoms. So this one here is going to be neon, and this one here is going to be helium.
What's the speed?
Oh, sorry.
No, you're fine. I need to remember what the Boltzmann distribution.
This one is more the number of molecules. Is that side? I might be wrong, but basically we're saying that the longer and the more like wide the curve is, the faster it's moving, and that means the lighter one that it's moving. Okay, any questions on that one? We can also look at this for the same element. So again, we can have a tall curve and then a long curve. But this one we can say that this is both like N2. Okay, and if that's the case, what we're looking at here is that temperature is different between the two. Okay, so the longer one is always going to be the one that's moving faster, and the taller one's going to be the one that's moving slower. So if one is at 25 degrees Celsius and the other one's at 100 degrees Celsius, which one's going to be the 100 and which one's going to be the 25? So the 100 is going to be this one here, and the 25 is going to be this tall one here. Okay, so she might have you, I know on your exam you have like a practice of ranking Boltzmann distribution stuff. So she might just have you do this for capture instead on your actual exam. Okay.
How much do I say it?
So she, like, I know on your practice exam, she has you ranking based off of molecular weight, but there's another application of Boltzmann distribution, so she might have you do it based off of temperature or something like that. She might just have you do it based on molecular weight again, but. Okay, what other questions do we have here?
How are you feeling about gas laws? Okay. Good little review about some math. Do you want to keep going? Yeah, okay. So then the only other gas laws that you have here is this rate equation. And so this just plays into effect of your VRMS. And so this is just saying that your slower rate will have a higher molecular weight. So you're able to determine the molecular weight of an unknown element if you know the rates of like a fusion for both of them. So if you need to solve that equation, you'll either be given 2 molecular weights and 1 rate, or you'll be given 2 rates and need to find the molecular weight. So it should be like straightforward and like, okay, I have 2 rates, or I have a rate and I'm looking for a weight. I need to use the one with the 2 rates for your formula.
And your rates are inverse, or not inverse, like the term on the
Yep. So rate 1 is rate 1, or is molecular weight down here, and then rate 2 is molecular weight 2 up here. Okay, how do we feel about chapter 5? Better? And I'll put together some like practice problems from each of these 2 and just kind of send that out as well. This will just be more of like a concept review, just kind of refresh your brain before you have to do math again. Okay, feel good about chapter 5. What was chapter 6?
everything is learned this entire thing.
What was chapter 6? I think that was more, is that more 7? Yeah, I think chapter 6 is more your light stuff. Right, did you have light in the last exam?
It was about light. About like frequent light. When it was seen.
Right, was that the next one?
Yeah.
I'll look on Heidi just to make sure.
That was like a big thing.
I know that I did when I took undergrad and stuff. My Chem 107 my Chem 107 was laid out slightly different. So we do things a little bit backwards. So I might just be thinking of that still. Yes, we started with the electromagnetic spectrum. Wow, there was a lot in this chapter. We have lecture videos for electromagnetic spectrum, photoelectric effect, the Bohr model, more energy level diagrams and quantum mechanics, quantum numbers and orbital energy, electron configurations, nuclear charge and ionic trends and electron configurations.
That's a lot.
Yeah, that's a lot of that. I thought it started with light. Okay. So this is
Light and yeah. Okay, what can you tell me about light and the atom? Let's start with the electromagnetic spectrum. Someone lay that out for me. This is low energy. And this is high energy. I think that's how they have it. Does anyone fill this in?
Low energy, microwave radio, so infrared.
Okay, so
My prediction was
I like infrared. Visible.
radio, lower energy than microwave. Okay.
What comes after visible?
Ultraviolet.
Good. And then
X-ray, and
X-rays.
then gamma.
Awesome. Okay, that's just good to know so that you know like which one's going to be more or higher in energy or lower in energy. Your lowest energy is going to be radio wave and your highest energy is going to be gamma rays. Someone have a question?
Is there like a phrase to remember that?
I don't know. I remember infrared, visible, and ultraviolet because infrared goes into red, and then RGB is the last one. Violet goes into violet. So those three I think are okay to memorize. I know that radio wave is the lowest, and then gamma rays is the highest. And so out of the other two, you just have to think of which one's going to be higher energy in terms of microwave rays. But if you put your food up to your radio, it's not going to cook. So you have to know that your microwaves have to be higher in energy than the radio.
Sure.
Any other questions on electromagnetic spectrum? I have questions.
Microwave, what is it? It excites the water molecules to heat things up, right?
Pretty much, yeah. Actually, Dr. Lee I think he did a TikTok of it. But he took the rotating thing out of the microwave and then he put a bar of chocolate and then put it on for like 30 seconds, I think. And then you can see where the waves in the peak of the wave appears in the bar of chocolate.
It's kind of cool.
Yeah, so basically it just sends like waves through it, and then I think it excites the water molecules, and then as a gas, right? As you increase your temperature of your water molecule, it's going to take it to a gas, and then it heats it up, and then you get more energy, and then you have hot food. Science. But yeah, the chocolate bar thing is cool. There's probably a whole bunch of people that have done it. So that's just a fun little movement experiment you can do yourself as well. Anything else?
The longer the waves, the lower the energy.
Awesome. Yep. So
The frequency, the lower the energy.
awesome. So longer wavelength equals lower energy. What did you say about frequency?
Higher frequency means a lower wavelength.
So we have
Higher energy, sorry,
Yep.
higher frequency.
so higher frequency equal to higher energy. So that means that longer wavelengths means what about frequency?
Lower the frequency.
Okay, so if we look at two examples, we can say which one's going to have a longer wavelength?
On the left.
Because long wavelength, what does that mean for frequency? Low frequency. What does that mean for energy?
Higher, lower energy.
Lower energy. This one has a short wavelength, which means its frequency is high. And that means its energy is high.
There's some equation I'm forgetting.
So there's actually two, and then you can combine them into one. Does anyone know what one equation is? Even the combined one.
8 equals. Y, is it like Y? Does it look like Y?
Not Y. Something that
Oh,
looks
it's
like
C,
it.
it's a C.
So C is equal to,
Speed of light.
yep, this is the speed of light. That's 3.00, I'm just going to do 8 meters per second. What equation involves C? There's a Greek letter involved. Yep, lambda times what? Yep, lambda v, right? So speed of light is C, which is equal to lambda, which is the wavelength, times v, which is the frequency. Your wavelength will be in meters and your frequency will be in 1/s, or 1/second, which is equal to hertz. Okay, and then your frequency times h is going to be equal to energy. And then this is your frequency, again, in 1/second or hertz. This is Planck's constant.
That's the 6.626.
That has a lot of units in it. Well, whatever energy, your energy unit. Yep. So your energy is in joules. So your Planck's constant is going to be in whatever units get you to joules. I believe it's on your formula sheet. Joules times seconds. So this is just in joules. Okay, and then does anyone know the combined equation? Can you tell them just this these two? The energy is
H times speed over V.
awesome. Not V.
Lambda.
Awesome. Okay, so energy is equal to hc over lambda. I believe Dr. Altimos gives you the energy and speed of light, so you're able to derive the hc over lambda. And that's just a good thing to know. If you have the energy of something, then you can immediately solve for the wavelength. You don't need to make that in between step. Also solve it for frequency.
They give you the constant on the cheat sheet, right?
Yep, they give you H and C for both of them. Any other questions?
Do they give us that? Like
That one I don't think they give you.
Lambda's wavelength.
Lambda is wavelength. Yep. And as like a pro tip, most wavelengths are going to be in nanometers. Does anyone know what the exponent is for nano? -9. So if you get something where it's like number, and then nanometers, that's like a good like 3 things, and then nanometers, that's good. And if you get something that's like 7.23 times 10 to the -7 meters, this means it'll be 723 nanometers. If you get anything like times 10 to the -7, that's going to be a good indication that you're going to be in nanometers, the way that you should be.
Your answer should be in millimeters.
Usually it'll be in nanometers. As long as it's in meters, it'll be counted. And also your frequency or your hertz will most likely be like 1 times 10 to the 14. That's usually a good indication of a hertz value. And energies are usually times 10 to the -19 joules. If you get somewhere around times 10 to the -19 as your exponent, you're on the right track. What other questions do we have about light? Feel okay with just this portion? Let's move into the atom. If we have the nucleus at the center and then your energy levels. what do we have to do to get from n is equal to 1 to get to n is equal to 3?
You need to absorb.
Good. Yep. Energy is absorbed.
So absorb it. In comparison to shorter wavelength. Or I guess no, we want to admit these.
Yep. So it won't emit any light. This one is like a light was shined onto an atom and it captured that light.
That we didn't let in.
Yep. But if we wanted to go from n is equal to 3 down to n is equal to 1, what happens there? Yep. Yep. Energy is lost. And a photon is emitted. Okay, so this is really important to remember. So when you go down in energy level, so as you go from n is equal to 3 to n is equal to 1, the atom loses energy. Okay, it goes back down to, if we go back down to n is equal to 1, what is that called? What is that like final state called?
Oh, science.
We're excited if we go from n is equal to 1 to n is equal to 3. What's the other way? If you fall from the sky, you're going to hit the what? The ground, right? So you're going to be in the ground state. Can energy be created or destroyed?
No.
No, right? So as the atom loses energy, what is gaining energy? Right? Because if the atom's losing something, something has to be gaining that energy. What gains that energy? Yep. So that photon, that light that is emitted, that's what has the energy going. So this is the same thing that gets released. Okay, so whatever energy is lost by the atom turns into the energy of the photon. So if you do anything with the equation, E is equal to negative 2. This one, where you're like showing the energy changing. If you start at a higher energy level and end up at a lower energy level, you end up with a negative energy. That's because the atom is losing that energy, and that makes sense. But we use the positive energy for the photon because the photon's energy will always be positive. Okay, equal and opposite. That's final and then initial. Okay, where did I lose people? Just ring the bell a little bit. Yes, okay. What other questions do we have about this portion? I think that's a big thing for this one. I don't think we need to talk about it.
Excited state is when it goes to.
So the excited state is just when it goes from something higher than the ground state. So if you have an electron at n is equal to 2 and it bumps up to n is equal to 3, that's an excited state.
Yep. Like when it's like since I was this it was something like like social I can find
yeah, I might need an example of it. And then I can let you know if that's important. Okay, anything else about ground state, excited state, fun stuff here? Okay. Big thing here is that to go from n is equal to 1 to n is equal to 3, we absorb energy. n is equal to 3 to n is equal to 1, we go down to, or we emit energy and energy is lost. Okay, 7 minutes. You want to just keep talking for 7 minutes? I'm going to just keep throwing information at you, see what sticks. Okay.
Isn't there one where it goes from like ground to like infinity? Isn't that, where's that like ionization one?
Yep, so that is an ionization energy. So if we have something where we'll talk about sodium, I'll call this the sodium atom. Does anyone know what period sodium sits in? Yeah. Does anyone know how many valence electrons sodium has? 1. Yep. So in n is equal to 3, we only have 1 electron. The rest are filled. You only have 2 in the first one because how many electrons? What's your first orbital you fill? The 1s2, right? How many? What's the maximum number of electrons in an s orbital? 2, right? So we're always filling that 1s2 orbital first, and then we have 8 electrons in the second, because what orbitals do we have in play in the second energy level? We have p. What else? S, right? How many electrons are in the s orbital? 2. How many are in the p? 6, right? So we have 2 from the s, 6 from the p, which means we have 8 total electrons we can fill. Then we go to energy level 3, and now we only have 1 in that 3s subshell. Okay, so your ionization energy is going to be the energy required to remove an electron. So we think that sodium's first ionization energy, or the ability to remove that first electron, is going to be high or low? It's going to be pretty low, right? It's in the 3rd subshell, so it's getting a little bit farther away from the nucleus. There's only 1, and that means we're only 1 electron away from looking like a noble gas, right? We're going to be isoelectronic. We're the same electrons as a noble gas, and sodium's going to be super happy. Okay, so first ionization energy is going to be fairly low. It'll be easy to remove that electron, and so then Na becomes Na+. Potassium is right underneath sodium on the periodic table. Is that going to be easier or harder to remove its first electron? It's going to be easier, right? Potassium has 1 more shell between the valence electron and the nucleus. Yep. So the farther away you get from the nucleus, the easier it is to pick off. Right? It's hard to get into the castle if you're really up close, but if you're really far away, it's kind of easy to start getting closer to the castle, right? So it's easy to kind of take those things away when they're far away, but as you get closer and closer, the nucleus is going to say, no, those are mine. It's going to want to hold on to those electrons. So the first ionization energy, lower. So okay, as we go across the periodic table, what happens generally to ionization energy? It increases, right? Usually as we go across, we see something where it's like this, and like this, then it drops down, again, down. So it kind of looks like that. Overall, right, we see a general increase in this direction. So it does get harder to remove those electrons as we go across.
But due to electron repulsion, due to some orbitals being half filled, due to some orbitals being fully filled, we do see that decrease in a couple of those ionization energies. Does anyone have any questions before we wrap up? You know, all troopers are saying pretty long. Okay, I think we did a lot. We probably did. Yes, we feel like that was helpful. You might feel a little brain dead. You okay? Okay. If you have any questions, please feel free to let me know. Send me an email. I will respond to it. I promise. Again, look out for a review session from me on Sunday at some point. And then I'll send a Zoom link for that one. This was recording, so I'll put that Zoom link up as well on YouTube and make an announcement about it. And I'll post these notes along with that as well, so you can review and cover today as well. Have a great rest of your Wednesday. Hope it's sleep. Get a good night's sleep. And we'll see you on Friday. Thanks so much. Okay.
There's one like this. It's on the table, like numbers for one.
Oh boy. I don't think you're gonna have to know the actual numbers. I think it'll be more of like how many transitions are available. Right, like counting. Okay, I don't know if I'm going from n is equals 4, I can go from n is equals 3, so n equals 1, and then it's 3, and n is equals 1, and then it's 2, right? Seeing how many transitions are possible, and then if you can tell the relative difference distance between them, then it's like, okay, I know that this has a short energy distance, so I know that that wavelength will be longer because its energy is lower.
Okay.
Does that make sense?
Kind of. So like how it has these numbers like in the green, I probably won't need to know that.
Probably don't know the actual numbers. No, you just need to be able to recognize and say, okay, this is a short energy difference. So if I have a small energy, then I know I'm going to have a longer wavelength and a shorter frequency. Okay, so like that, just that relationship and not really the actual numbers.
Okay. And then do you think like something like how it's like how it said like going from like the energy level like 3 to 1 and using like the combined stuff probably
you could do something like that. If she gave you like the energy of energy 3 is cookie, and then the energy of energy 1 was 1, what's the wavelength, right? Then you can say, okay, the difference between those two is 2. So I know that I can then say, okay, 2 is equal to h times c, which is divided by the wavelength. I get the wavelength, we can solve for wavelength that way. So that I think so, but is a potential, but I don't think you need to know the actual distance between them.
okay. And then like since I know like each like level is like a different, like they're not all the same, so it's like so like from 4 to 3 is long. Like when you say long wavelength, do you mean like big? Like
Yes.
long?
Yep.
Okay.
Yep. So more like radio wave, more like microwave side.
Okay.
Rather than from 4 to 1, we have a long energy difference, or we have a big energy difference. That means we're gonna have a lot of energy. So if we have a lot of energy, what side is that going to be on? Yeah, more towards the end. Then it's like woo.
Okay. So when it says short, is it like woo, and long is like
Yep. Yep. Because if we're looking at kind of trying to draw it. So if we're looking at like this. Oh, yeah. Right. As we go from here to here, we have a lot of energy. So then our photon is going to look like this. Okay. A lot of energy, short wavelength, right? Because each wavelength is just every time you come back is one time, right? So wavelength like this, start here and then get back to that point. So think about here again, right? That's wavelength. But if we go from here to here, you might only get that much.
Okay.
Okay, so it's short energy, so you have less stuff.
Okay. Okay.
Yes, it does. I don't know if it's better. Yeah. Great job.
He's back.
Did you have any more questions?
Think so.
Okay.
What part did I miss?
We just talked about like submitting and absorbing and stuff a little bit more. But I Zoom recorded it and so I'll post it. If you really want to look at it, you can check it out as well.
Thank you.
You were it was totally it's going to be a lot of them. I was checking out myself.
Zoom, 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 zoom.
I had to go left my iPad converted to death. So maybe it's a good time now because I can't take more notes anyway.